How many highly developed civilizations are there in the universe? The Drake formula: where are all the aliens if the cosmos is overflowing with them? Enrico Fermi, an Italian physicist, is rumored to have posed this query to himself during a discussion about the likelihood of encountering advanced extraterrestrial life. It seems that the only way to provide an explanation is to use your imagination and aim to write fantastic science fiction. Nevertheless, as the film progresses, we will find that this question is not as absurd as it first appears to be. Someone attempted to answer it quantitatively instead, making a valiant effort to remain within the purview of pure scientific speculation. He accomplished this by developing an equation that, when solved, would give us a precise estimate of the number of other civilizations that live beside us in this peculiar condominium that may be our galaxy. One of the pioneers in the radio search for extraterrestrial intelligence is astronomer Frank Drake. The Drake equation, which he created, is a well-known formula that can be used to estimate the number of advanced civilizations that may exist in our galaxy. In November 1961, at a meeting at Green Bank, the equation was first presented. The goal of the program was to start a meaningful conversation about the chances of finding extraterrestrial intelligence via radio technology. Drake's formula sought to illustrate through a mathematical relationship the particular elements that are crucial to the emergence and advancement of advanced civilizations throughout the cosmos. As will be seen, each term in the equation represents a crucial step in the development of a civilization, and the numbers that are produced have only theoretical significance. Given that the majority of the values that can be assigned to the various parameters lack experimental relevance and are therefore merely theoretical, it should not be forgotten that any evaluation that can be conducted in such a setting appears to be exclusively probabilistic. Although a clear answer to this problem is not now feasible, it is unquestionably of scientific interest because it effectively demonstrates the possibility of this kind of research. Drake's theory is based on the idea that the number of advanced civilizations in our galaxy that may exist and have the desire and ability to communicate over interstellar distances can be fairly estimated using the equation below. N is the estimated number of intelligent civilizations that are present in our galaxy and are able to communicate with one another. It is important to remember that in this context, we are discussing civilization rather than life in its broadest sense. Drake presumably drew this difference because it is currently technologically impossible to investigate whether life exists elsewhere for oneself. Therefore, the only realistic chance of learning whether, for instance, there is a civilization on Vega depends entirely on the possibility of receiving a phone call from that planet, a message structured in such a way as to clearly indicate that life has not only taken root there, but has also evolved to the point where it can communicate its presence. N star stands for the number of stars in our galaxy, which is expected to be in the range of 200 billion stars that are more or less comparable to our Sun. This enormous number is the primary cause of even the hope of not being alone being among the last to perish. The most optimistic theory is N equals N star, which holds that intelligent life has developed around all stars. But, given where our knowledge stands right now, it is hard to sustain this theory on the grounds of good physical and historical political sense. In a different version of Drake's equation, the average annual rate of star formation over the whole history of the Milky Way appears in place of N star. R is calculated by dividing the number of galactic stars by the galaxy's age. Because it is derived from the number of stars that are actually extant in the Milky Way's age, which is currently considered to be 20, it is the only parameter on which hazard calculations are achievable. The percentage of stars with planetary systems is denoted by the symbol FP. Astronomers are constantly revising this definition as they discover more and more conclusive evidence of the existence of planets orbiting many of the studied stars, thanks to missions like the satellites Kepler, GAIA, TESS, and other similar missions. This is made possible in part by the significant boost provided by new technologies. Yet because to issues with celestial mechanics and reciprocal perturbations, double stars that are at least 50% massive have trouble maintaining planetary systems. Yet we should not be pessimistic because other considerations will then rule out dual or many systems. One may assume that Fp is equal to 0.5, meaning that half of the stars have planetary systems. Ne stands for the portion of the fraction of these planets that have conditions similar to ours. The subscript E stands for Earth, making them potentially conducive to the emergence of life, a distance from their star that can provide a quantity of heat and light that is neither scarce nor too intense, i.e. that places it in what is typically referred to as the habitable zone, and a region of the planetary system where the tidal effects of the estimation of Ne is more challenging. Thus we will need the assistance of space missions like Kepler, TESS, GAIA, and others. Giant, frequently gaseous planets are frequently found in close proximity to the central stars, as of yet. As a result of their smaller size, several rocky planets have also been found, however with greater difficulty than the first. Hence, Ne greatly depends on the kind of star. The useful planets should cluster close to the small, cold ones because they have a highly constrained habitable zone. Yet in this instance, the tidal force would block them, much like the Moon does with the Earth, and they would be doomed to always present the same face to the main star, with dramatic results that are obviously clear. Huge stars provide more space, but have considerably shorter lifespans, and so on. Each star has its unique urbanization issues. This parameter's reasonable estimate might be 1, i.e. one habitable planet for each star with planetary system. The percentage of habitable planets, or FV, where life actually arises and progresses towards extremely complex forms. This variable accounts for how many of these planets capable of supporting life were actually able to do so. The physical, chemical, and biological path that leads to life's development can be interrupted or diverted by a whole series of factors, some of which are currently known and many of which are unknown. Life is a complex phenomenon, subject to too many variables, and maybe more so than any other event within our universe. When we consider the former, we cannot help but consider the impact of one or more asteroids the size of the one that is thought to have abruptly ended the existence of dinosaurs on Earth. A reasonable estimation might result in a number of 0.2, i.e. 1 planet out of 5 would allow life to evolve. Fi is the percentage of these planets where intelligent life first appears. This phrase must consider how many of all those fortunate planets that have produced life have been able to protect it and allow it to develop into intelligent life. What genuinely drives the evolution of life towards intelligence? It takes time, there are relatively stable climatic conditions, and few external disasters, falling asteroids, exploding supernovae, etc. The percentage of planets where intelligent life shows an interest in interplanetary communication is called FC. His estimate is likewise rather complicated, a belt of asteroids so dense that it would be impossible to use orbital telescopes or go to space. The value of this proportion may change due to factors like a considerably heavier cloud cover, cosmic modesty and intolerance towards others' agoraphobia, or just a stage of human growth that is not technologically ready for interplanetary contact. The typical lifespan of a technologically advanced society is D years. History teaches us that civilizations are created, develop, reach a cultural apogee, and experience economic prosperity. Yet it also teaches us that sooner or later, these civilizations experience the calamity of frequently self-destructive fall. We would never be aware of the existence of an alien civilization that was willing to communicate with other alien civilizations strewn across the cosmos, but in its evolutionary hysteria, the nightmare of a total war was opposed to either obliterate the entire race or leave a few survivors unable for various reasons to resume a discourse oriented towards cosmic communication. While there is no experimental data that enables for a sufficiently accurate assessment of the parameter's value to be produced, it should be highlighted that the calculation's most sensitive component is precisely the clear difficulty in assigning adequately approximate values to the parameters. Everyone can test their own assumptions and practice computing the value of n by inputting more or less trustworthy data based on the findings of the most recent astronomical and exobiological discoveries. The astonishing truth is that, in many circumstances, the estimate leads to a probability of the existence of intelligent life in our galaxy that is extremely near to 1, regardless of whether one is essentially pessimistic or optimistic. Following significant astronomical discoveries in recent years, it has been gradually possible to provide some variables increasingly exact values. 3 of the Drake equation's parameters, however, are still only theoretical. But, according to some academics, it is possible to provide a pretty accurate estimate of the value of each individual element in the Drake equation. This estimate seems to convince some people that life is present in other places while persuading many others that it is not. The most glaring fault in this equation is actually its greatest strength. It draws a lot of serious academics who are able to provide incredibly diverse and frequently sharply divergent numerical assessments on the potential worth of its output due to its seeming scientific rigor. The orbital information and mass of exoplanets discovered so far are both steadily growing, and these data are directly related to the development of new and more advanced instrumental technologies that may soon enable us to directly detect the presence of terrestrial-type planets. Yet the scientific community is mostly in agreement that terrestrial planets are frequently found circling solar-class stars, spectral class G2V of the Hertzsprung-Russell diagram. Similar arguments support the hypothesis that planets with orbits stable enough to support the presence of liquid water essential for the emergence and development of life exist on the main sequence stars of a spectral class roughly similar to that of the Sun. According to Drake's equation, civilization will only exist in environments that are similar to or barely different from our own. If one considered this equation and the theory behind it as a multiplication of unknowns, the assertion that they are scientific might appear to be in doubt. However, doing so would be a mistake because it would ignore the method that was used to conduct the search for the value of each of its individual terms, which was chosen specifically to preserve the accuracy of the scientific method. Be sure to subscribe to the channel. By giving us a like and pressing the bell, you can help us create ever better products.